Welcome everyone, and good morning, and welcome to another JKMRC Friday seminar series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to acknowledge the traditional owners and the custodians of the land on which we meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contributions to the Australian and global society. So today it's my great pleasure to welcome Dr. Nurassyl Battalgazy. Nurassyl recently completed his PhD here at the Sustainable Minerals Institute, specializing in applying machine learning and deep learning in resource estimation. He's currently a geoscience data analyst at IMDEX, working on the Battalgazy project. With experience in resource estimation, structural mapping, and spatial modeling, Nurassyl has contributed to academic research and participated in many industry challenges, including the Future Explorers Challenge, where he applied a deep learning framework for mineral targeting. He has also published in leading journals and presented at many international conferences. So today his talk will be about unlocking the potential of AI in resource assessment. Please join me in welcoming Nurassyl.
Thank you. Thank you. Thank you very much, and good morning all. Thanks for coming and those who are joining by Zoom. And today I'm going to talk about some AI fancy topic, but it's not actually fancy. It's just simple, but the name is fancy. So today's, oh wait, this one is the best one. This is working? Yeah. Oh, yeah. A little bit about myself. Christy already gave the introduction, but yeah, I'm originally from Kazakhstan. Did my master's degree in mining engineering in 2017, where I started to know more about mining industry. Was doing a lot of research in my university in Kazakhstan, Nazarbayev University, related with geostatistics. And then had a chance to work in open pit gold mine in Kazzinc, one of the actives of the Kazzinc. Then in 2020, I started my PhD here at BRC, SMI. And currently I'm working as a geoscience data analyst at IMDEX here in Brisbane. So today's content will be about AI, deep learning, and specifically convolutional neural network. And I'll just remind some terminologies at the beginning. And we will talk about deep learning in image analysis. And then we will go how we could implement it in grade control estimation, which was the main idea of my PhD. And then research results from the PhD, what kind of challenges AI faces when applied to these kind of tasks. And also recently I had a chance to participate in brownfield exploration. So I'll talk a little bit about this topic as well, and then what kind of challenges we face there. And then a little bit about future of AI in resource assessment. So let's just remind ourselves what is AI, like just to go through AI terminology. AI is basically any machine or system that can imitate the human intelligence. Machine learning is a subset of AI that enables systems to learn from the data. Neural network is imitating the human brain, learning through the neural networks. And then deep learning is a subset or further subset of machine learning where you have many layers of neural network. Hence, the name is deep. And then generative AI, which is a branch of AI focused on creating some text, image, audio, data, basically new content. And generative AI, as you can see from the image on the right side, it actually uses a lot of deep learning, large deep learning neural networks to create its own text or image or music. ChatGPT is a good example. So before starting to talk about deep learning, let's just go through very simple geostatistics I do understand it's a general audience, so I'll just go very simple. So let's imagine we have a point in 2D maps. This is actually pixel points. And let's give shades from white to black. So you have and pixel numbers from 0 to 255. So you can pick any of the color. And then let's do kriging on this 2D map. So it will do something like this. It will smooth it because of the smoothing effect. But the reality is in resource grade, even grade control resource estimation, you have a very small amount of data from existing ground truth. So it's not even 0.1%. It's way, way less. So it's really hard to understand what is happening in between these points because it could be anything, but we are making it average. So what happens if I'm gonna just enlarge the pixels? Does it give you any idea what is happening here, for example? It's really hard, isn't it? If I'm gonna give you more pixels, can you guess what could be, what is the image? What is the image here? Can you guess, any of you? Yes, it is cat. I was thinking you're gonna not guess it, but yeah, it's a cat. But you can see actually it is really different than what we are seeing here in the kriging. But you can get actually some of the bits which correlates well. But you can see on the right side, this one is more or less brown color, and you have no air here because it was taking exactly from somewhere here. But surrounding is black. So this is one of the things that, one of the challenges that geologists face. After giving a quite simple example of geostatistics or result, just a 2D estimation, we can, I think it's better to dive into how deep learning works in image analysis, because when we are talking about image analysis, it's pixels, and pixels is the numbers. And in resource estimation, we also work with the numbers. So deep learning, I'm going to talk about convolutional neural network, which is a class of neural networks that commonly used in computer vision tasks. And mainly it's used for image classification, segmentation, object detection, and also it can classify in one image different objects. Plus, one of the interesting part is image reconstruction, which was, I think, when I started to realize it could be implemented in resource estimation. On the right side, you have a deep learning predicted faces from low resolution on the top. You can see it's 16 to 16 pixel input. And on the bottom, you have a high quality ground truth images. And then this one on the middle is a predicted faces. As you can see, these pixels actually imitate drill hole samples, because what you are seeing is actually very low resolution pixels. And we can use deep learning to create something more realistic, not more realistic, but something that is reasonable. And how deep learning works. So you have millions of pairs of images with input and output. And you train the model by feeding this training data. And after getting all the weights in the neural network, when you apply it to the new data, it can predict by learning from whatever it learned from the training data. So the idea was to use it in a similar cases, but in terms of resource estimation. And during my PhD, we started to do some work with 2D maps by using, I forgot the name of that data, but it's from, I forgot the name of the, if you can remind me. Yeah. yeah, micro XRF image. Yeah, and yeah, but that's how we started doing, I mean, exploring the convolutional neural networks. This bit is a little bit hard to explain, but I'll go through with simple words. So basically, convolutional neural network consists of 4 layers. So on the right side, it's input, where you use the input image. And then you have a main part with the feature learning, convolutional, and pooling layers. And then you have a classic neural network. And then you have, at the end, you have the output, which could be classification or continuous variables. So you can see it actually use in convolutional layer, in kernel convolutional layers, you use filters or kernels, which actually slices among the pixels and gets some information. So you have a different types of filters, kernels that can be used to learn some, for example, edges of the images. So it can get some patterns, some knowledge. And by using number of convolutional layers and pooling layers in different combinations, you can actually train the model to learn something from the data, like patterns. And the pooling layer is used to decrease the size of the image to make less, to make it efficient, because the images are a lot of pixels and you want to decrease the size of the images. And you can use the maximum or average pooling layer, where you take, for example, in this case, you have 3x3 filter with maximum. So it takes the maximum of each 9 pixels. So you decrease the size of the image. And this is convolutional neural network architecture from my research, which was based on this network. In this case, you have 64, 64, 64 pixel image, which we will talk later, but it's input data. You can see it imitates some drill hole pixels. And I will talk a little bit later how we create this image. And then you have on the output, you have a block model. In this case, it is 888 pixel averaged cells. So basically, every cell is actually average of 8 pixels, if it does make sense. And then talking about the input data, so how we could actually convert a drill hole sample data into the world of image. So you can actually create grids with a different size of the pixels or cells, and you can assign the numbers, or you can actually composite and then reassign it back to pixels. That's how the input can be converted. So in my PhD, we used a 3D micro city image of carbonate rock, and you can see it actually have some geological features in it. And we decided to work with this data. And the idea is to imitate drill holes from this high resolution data and imitate block model by averaging some of the pixels to make a block model ground truth. So basically you have a pairs of data with input and output. And the grade is actually from around 60 to 150, which is actually pixel values. It's not a real grade. And the data split. So before training, you split the data, and basically you have two different state where you use training data as to train the model. So you test data on a validation data. It's called test data here. And you have a holdout data, which will be used to evaluate the final performance of the trained model. So it's completely unseen data. So basically we are splitting it and taking one holdout data where we can use it at the end of the model when we are satisfied with the validation. So the idea is to split it into holdout, drill hole, and block model, and training drill hole and block model. This is just the statistics showing what it looks like. I said it 1 meter because I'm imitating 1 pixel is 1 meter. And then we train it by monitoring the training process. And we are using several measurements to monitor it. So one of the main ones is a mean squared error, regression score. And then we used as well peak signal to noise ratio and structural similarity index to understand, because it is mainly used in image analysis, image reconstruction. That's why I started to understand, like, okay, maybe we need to as well use it, even though I don't think it's used in geostatistics. And also histogram intersection, where you compare the distribution of the values predicted and ground truth. And during the training, you can overfit, you can underfit. So we are trying to find the golden middle. And from my experience, the golden middle is somewhere here when you see that measurements are pretty flat, horizontal. So if you go further and you use one of the last training epochs, it will overfit definitely. And that's why you try to use something in here where everything is flat. So when you are training, you also train with a chunk of data, very small chunk of data. In this case, it was 64 pixels. That's why when you are predicting on a new data, you have to put it back. So when you are predicting very small chunks, then you have to put it back to the original one. That's why you can actually take chunks that has intersection with the previous chunks. So you can put it back by averaging the overlaps and get back the block model again. And this is the results. So deep learning result here on the right side. And I also did ordinary kriging in single domain, where we could see why I'm also classifying into domains, because I started to see there's a different domains. That's why I did another results with multi-domains. So basically classifying into 3 domains and doing interpolation within the domains. And you can see it actually has hard boundaries in it. But okay in single domain was okay. Then this is the comparison in one of the slices along the y-axis. And on the top is the ground truth. And you have a block model generated by deep learning, okay, block model, ordinary kriging block model, and okay in multi-block, multi-domains. And you can see actually it, the results are, I mean, good. I think so. Deep learning is maybe less better than ordinary kriging in single domain, but it is capable of actually showing good results as ordinary kriging. You can see the regression score is almost similar, correlation, mean squared error, and histogram intersection score. And okay in multi-domain, as you can see, is worse than the rest of the data, the results. So one of the challenges that I saw during my PhD is first working with the real world industry data, because what happens is in real world industry data, the samples, the data is sparse, it's irregular. Sometimes you have more data in one place and very less data on the other places. You might have missing data as well. So when you are implementing this kind of methodology, which is only fitting in mining projects where you have data input and output. So if you are questioning what could be the output, it could be a reconciliated block model, for example, and you can use it for train the model and then use it in the next steps when you are having a new data set. You can rapidly create a block model. And also, I wanted to include that deep learning might fail as well. So it's not something that will do perfectly all the block models, and it depends, very dependent on data itself. So when we are working with deep learning, we should be very careful with our data set because we need to prepare the data so deep learning will understand it. A lot of processing happens before training the model. So the future work that I'm aiming to do it is exploring the application of convolutional neural networks in open pit mines with regular grid RC data. And I'm seeking for the data. And also another part is adding value. So using or integrating structural information and probably geological model like lithology information, etc. And this is a small bit of how you could implement structural information in deep learning framework. So you have two data sets. The first one is continuous variables. The second one is structural information, which is basically binary information with either 0 and 255, or you can level it and make it 0 to 1. So you have only two options here in continuous variables. And you can see this is a block model, which is very high resolution block model, actually 1 pixel, 1 block model, and you have a fault crossing it. And one of the objectives of my PhD was to able to integrate additional information. In this case, it's a synthetic structural information where I sliced the image and displaced the sections. And you can use multi-input convolutional neural network. In this case, it's only 2, but you can add it 3, 4, so several inputs. And this is one of the examples with different spacing as an input. This is the ground truth and the results by convolutional neural network. It's unfair, I know, to compare radial basis function and kriging with something that has way more knowledge, but it's just for comparison how it works with and without. So you can see it actually, convolutional neural network results were giving some kind of a fault. But using different types of fault is another question. In this case, we were using very simple angled fault, which was the same everywhere. But in reality, faults might be in different directions and sometimes very complex. But yeah, I'm challenging myself to use in the future structural information to be able to use it at one point. So the next topic is about deep learning in brownfield exploration. I'm not really expert in this sphere, but I was just trying to share my experience participating in a challenge. So this year, probably 4 months ago, we won a challenge called Future Explorers Challenge. And it was organized by Dundee Precious Metals and Human AI. So the idea was they will provide all the data to candidates, and then they will look through all data. Whatever, how they can use it, it doesn't matter. But some very experienced geologists were taking it part, and then some unexperienced like myself were also joining this challenge. And it was quite interesting because I realized I could use this convolutional neural network as well in exploration tasks, because what does convolutional neural network is you need a training data with inputs and outputs. So my idea was to use convolutional neural network. Unfortunately, I cannot provide all the information about this challenge, but this is how the basic idea was. So I was using a different sources of information, but the main logic was what the size of the data. Is it covering all the bits of exploration, brownfield exploration area, or it is covering just a small bits? So the logic was to take the biggest ones. So the magnetics and gravity and resistivity was one of the biggest ones. And I started to use it to train the model based on block model. So you are taking a small bits. I will show in the next slides. Just the imitation of mining. It's a mining area, and let's imagine that we have all this geophysical data in this area. So what you are doing is you are taking input data from here, which is those three geophysical data sets, and you have also block model. Or you have very dense resource grade control data set, and you can create your own block model and then use it to train the model. So you are basically giving geophysical data and predicting new block model, not new model, but you are training on the block model. And then you can use it for the rest of the area where you have geophysical parameters. And this is how convolutional neural network works for this kind of tasks, where you have three inputs. In this case, it's magnetics, gravity, and resistivity. It was a copper and gold deposit. So I did two deep learning models for copper and gold as well. And the idea was to look the correlation after. So you are training different models on different minerals. So copper had a different model, and gold had a separate model. So, and then after, when you are predicting on new zones, you can actually compare the correlation, how you ended up, because there's a correlation between copper and gold. So you can actually compare after. And it was quite good. And we were showing it to DPM geologists, and they were happy. But they were asking a lot of questions as well. And one of the questions is to use, are we capable of using structural information, faults? And yeah, because we had a time constraints, we were happy with this one. But in the future, I guess one of the objectives is to be able to use some other additional information, which is very helpful. And it's a matter of how you convert the data into workable format. So convolutional neural network can take it and process it. Yeah, that's what I already said. But yeah, you can predict on the rest of the data, and you can get some data, which we don't know what is it, but yeah, it could be high grade or low grade. So we can actually classify it as well. So the main challenges of this challenge for me was to work with the data complexity, because sorry, this is not about the challenge. This is how we could use it. So we can actually use its ability to work with grid-like data set. In this case, in image world, it's pixels, but in exploration world, it could be a block model. Anything grid-like data sets. And then we can customize or do some research on creating specific designed convolutional neural network architectures to learn these patterns, the complexities, the correlation, and then we can apply it to wherever we have input data sets. But the validation is a bit hard to do. And the only way I think validation might happen is to use block model and hide it from your model. And then when you are ready to, after training, when the model is ready, you could validate on existing bit where you have a block model. And the challenges, as I said, it's a data complexity. Because even, for example, if we are talking about structural information, is binary, like converting into binary system, gonna work? Or we can actually look at the deep and azimuth and create another set of data sets with a different numbers, which represents deep, which represents azimuth, etc. Scarcity of the data, sometimes it's not enough just to train the model. It didn't learn a lot. Data dependency, so in grade control estimation, the data dependency is quite obvious, but here, data dependency means you cannot apply it to, if you are missing one of the inputs, you cannot already apply it because it will lose a lot of weights, a lot of information. And future work that I will aim is working with some projects where they are interested to provide their exploration data set, or they are looking for targeting new mineralization. And also one of the values that I want to use is a structural information. It's the same as before. And a little bit about AI, AI and resources assessment in near future. I guess from this figure, you can see we are actually getting a lot of data set, and most of the time, a big chunk of it we are not using it. So I guess AI provides you ability to include all of this data if it is related to, let's say, resource assessment, and we can increase the productivity because it's rapid. You can constantly update it, so it will learn constantly. You can get some more insights you've never thought about. But there's also risk, a black box. You don't know what's happening really. Sometimes it doesn't give you a logic why it's showing this. So it's a big risk. But I guess when you are working with local geologists, they might help you a lot to understand this anomaly, or to understand the results that you don't think is good or right. And this is a picture from my PhD, where I was thinking to use AI in this is basically showing all the improvements when you are using AI, and how these blue ones are the resource assessment related or mining related, I guess. Yeah, increased resource recovery, improved mine planning, data integration into resource assessment, rapid modeling, and higher accuracy, which is under question. Aligning with ESG goals, faster and accurate decision making, lower emissions. That's how I see the AI in near future, not near future, maybe in 10 years or 20 years, but it's progressing rapidly. If we're looking 2 years back, no one knew about ChatGPT, but now it can make some jokes on a human level, intelligence level. Some of them are really funny. Yeah, so that's the end of my presentation. But if you have any questions, we have a big amount of time to ask and have a conversation. Yeah. Thank you very much.
Thank you very much, Nurassyl. That was very interesting. And thank you for your attempt to make it more understandable for us non-geo people as well. It was really interesting. So do we have any questions, Nick?
Hi, thank you. So the question about the predictability when you have, say, multi-element geochemistry, and you'll essentially get an orientation in 3D of where that data goes. But then we talk about structural data.
Yep.
If we're talking about a fault, is trying to map out that. But if you're talking about measured structural data, how are you going to apply, say, orientation data to a single point in your model? And how do you, I suppose, give that the flexibility to relate to the geochemistry?
So when we are talking about the structural information here, for example, we can model the structural model first and then convert it into image. So when, for example, this one is already, I mean, this is the ground truth, but it has a fold in it. And what we can do is we can create a structural model where we know where it passes. And when we are using the chunk of data, you can actually make all these pixels where it's crossing, let's say 1, and the rest is 0.
Yeah, but then how do you add in orientation data
That's
to
what I was talking.
pre-existing?
Yeah, true. It's a good question. That's what I was talking. When we are using the structural information, we could use either by this way, which was one of the results that I got. It was working, but I had an idea to use actually deep and azimuth information with a different set of 3D images. So you have one image with azimuth only and one image with deep, for example. And yeah, that's the idea of using it. But yeah, it's still a big question for me as well. But using just a binary information was giving me some good results. But this structural fault was very simple. It's just one angle, one deep along the data.
Yeah, so one way might be to do that would be to apply, say, a Flynn diagram type model where you had oblate or prolate ellipsoids to the data point, and that would give it actually some directional probability based on the data that was collected, say, off the drill core. That would be one way to do that sort of stuff.
It's true, and there's so many ways actually you can use it, because it's all about like how you can convert the information into images. So yeah, I think there are like many ways to integrate or convert into the image and use it. But yeah, I think it's doable.
Any other questions? Okay, many.
Thanks, Nura. That was great. Quick question. You kept specifying grid-like, but what happens if it's not grid-like?
Can you give me an example? What is not like grid-like information?
I guess exploration data that's not in a grid.
Okay, for instance, in this Chelopech, in Chelopech project, that they were giving geophysical data, and some of them are just point-based. So basically, you have to interpolate it to make it grid-like. So let's say you have very dense points, but you can make a big cell out of it. So you can average, or you can do some interpolation techniques to create a grid-like information out of the points. Or you can change the points to cell itself and use it as a grid-like information. I think so, yeah.
I got one. Great talk, Nurassyl. Some really cool stuff. I'm just curious to know how computationally intensive this application is. Like, there's lots of modeling and simulations involved. And then further upon this question, how easy it would be for a user in like going forward in the future to apply this? Is it just another desktop software, or how would you integrate that in applications?
Thank you very much. So the first one, how computationally expensive? It depends on the data itself. But in my case, even using this small image, 3D image, I couldn't run on my laptop. So I used Google Collaboration, Jupyter Notebooks, for example, to run it. And I was using really high performing processings. In what Google Collaboration was giving me, I was using the highest one. But yeah, if I did in my laptop, it would take days, but in that one, you can do it in hours. So it's a good one. And in terms of usability, how, let's say, in the near future, if geologists going to use it, how they're going to use, it's a good question. You're asking like an investor. I think everything is code related, so you have to make it ready to the users to be able to click a couple of times, change a couple of parameters, and run it. I think you can make it more smooth, so it's easy to use. Yeah, but for now it's code based.
Thanks, Nurassyl. I enjoyed that talk. I have a bunch of questions, but I'm not going to ask them all. I'm only going to ask one. But I'm going to preface the question with the plug. First of all, congratulations on winning that award.
Oh,
That was great. And the plug part is to say that SMI Memorial Day is coming up, and for the plug, would have been more effective if I could remember the date, but it is coming up, I think, in late October, early November. 15th of November. Thank you, whoever said that. The reason I'm mentioning that is that you won the Dan Alexander Award for for innovation that had potential to be commercialized, and this was, a lot of this work was really the topic of that.
Yeah.
So my question is, how did that award contribute to your success and then going on to winning a prize? I'm hoping you're not going to say, oh, they have no connection whatsoever.
No, it has a connection, because I'm giving up my PhD laptop, and I need to buy another one to continue to do my research. But yeah, it also gave me some resources to buy the computer power, because you subscribe to the Google collaboration and monthly payment, or for the conferences that I'm going as well. So in Perth, it was really good to get some feedback from people, a lot of critics, but I like the questions because it challenges you. So yeah, the resources given by Price was very useful. Yeah, and I'm still using it.
And I'm going to ask, I'm going to avoid my other questions that aren't on this topic, but keep on that topic. And that was that, what was it what aspect of your work on that competition, which was working on Chelopech, was it?
Yeah.
What aspect of your work on that, in that competition, led to the prize? And because I got the impression that you weren't allowed to show us the kind of killer
Yeah.
diagrams that
Yeah.
that got them over the side, but I'd love to hear what it was, what their feedback was about what aspect of the work of you and your partner on the project
So
led to you winning.
during this challenge, we had a chance to talk with geologists, local geologists, exploration geologists, and when we showed our methodology and what kind of data we used, what extent we used the data, they were amazed. I think they never seen like neural network usage in exploration. That's why maybe it was taking their attention. And the thing that we used the whole geophysical parameters was good, because we were asking ourselves a lot of questions like, what is gravity, how it impacts to the gold or copper. And after a lot of questions from our side, when they said, okay, these three are the main ones, and then we used these three ones, they were pretty happy with it. I think, yeah, just it's not only fancy names, but I think convolutional neural network is capable of doing some spatial prediction, because we were also showing the validation, how it was trained, how we were satisfied, and we used satisfied model to the rest of the area, and we gave, I think, 4 targets locations. One of them was big one. That's why and also we used another methodology from my teammate, and we were matching in one place. So we were more sure on that location. So we gave them as a main target location. Yeah, it was good and interesting. A lot to learn yet, but yeah, it's I guess a interesting start. Thanks for the question.
We have a question from our online audience here. Henrik writes, thank you very much for the presentation. I have one question. Is there a way to gain any information on probability from an AI-generated model like you would from a simulated model with multiple realizations?
That's a good question. And the question was actually from my PhD as well. And one of the ideas is it sounds really different, but we can use different epochs. So when you're training the model, you use different weights of the neural network. When you do iterations, you might have different models. So you can actually use a lot of epochs, but not overfitted models, but somewhere in the golden middle, you can have like 10 or hundreds of epochs that you can use to predict and get some variability and use it. But one of the bad side is it's not consistent. It's going to be different because when we are doing probabilistic, we use, let's say, random numbers, but here it's totally different. You have totally different models, and we don't know like how much of the data is used, how many times. So yeah, but one of the ways is to use, and I was suggesting as a future work for the next PhD project to be able to use that and explore it.
Yeah, any other questions? Okay.
Just another one. So in future, are we gonna see this as a replacement of kriging, or are we just gonna basically say it's just some another method and then compare kriging, indicator kriging, or whatsoever?
Yeah, I don't think we can replace any traditional methods, but it could be a good tool to add in a resource estimation world. If you have a amount of data enough to train the model, why not? To give you some insights, to give you rapid decision making. But I don't think we can replace traditional methods, because that's how I showed the cat, because we never know what is happening. Yeah. And kriging gives you, I think, the righteous answer.
I think ground truth. Yeah, right.
Sorry.
Cool. Thanks.
Any other questions? Rick? Getting my steps in today. Okay.
I wanted to build on that question because it was a good one. Yeah, stop there. Because one of the things that strikes me, and actually you didn't really talk about it, but it was part of your project, was that the reason that those predicted faces, well, some of them are kind of funny, but overall they're pretty good.
Yeah.
The reason they work is that with what this approach can do that kriging and most other geostatistical approaches, in fact, all as far as I know, can't do, is to learn about what real patterns look like.
Yeah.
In the way, and there are real geological patterns that people who do geoscientific interpretations have imprinted in their mind, just like a CNN does, and just like a deep learning algorithm does. And that when they have a sparse data set of observations in a map or anything like that, they're pouring their accumulated knowledge into that area in order to actually produce a map. That's exact, the mapping exercise could be really, summarized with that diagram on the right, where you've got sparse data, preconceived notions, and a prediction in the middle. Preconceived, or, you might call it enlightened speculation rather than preconceived notions, which sounds a little bit bad. But to me, it seems that the potential to do that with deep learning is the main difference, and maybe speed, I don't know, between you know, a geostatistical approach to prediction of whatever you want to predict, and a deep learning approach. And I'd be interested to hear your thoughts on that and how it could be, you know, how it could be exploited to a greater extent.
Yeah, it's a good, was it question, but it's a good thoughts, because I will start from the black box, so we don't understand what's happening really, but once it's trained, once it's validated, it is actually a good tool to use. For example, even here, some faces, you don't see actually there is a glass, but the prediction showed you glass. And maybe you were looking for the glass, and by geostatistics, you might not see it. That's the privilege of using deep learning, but it's data dependent. So basically, you should have a data with a block model that was done by geostatistics and use it to train the model. So basically, if you are even training on the ground truth, which is based on geostatistics, it's not going to be far different because we are using geostatistical data, interpolated data. But yes, if we know with a way higher resolution, it will be useful. And yeah, as I showed, the results with ordinary kriging, for example, was not much different. But the difference here is the time spent on estimating. So it's rapid, but you have to spend some time to train it. But if it is automated, like Smooth, you are getting the data. You have a block model, you have grid control data. You can train the model constantly, and you don't spend on time training the model before applying, because you have already trained model and you can apply and get the results very rapidly. Yeah, but yeah, there's a difference, a big difference.
Can I just add a comment here, and it might sound like a criticism, but it's not. But this diagram you've got here in particular is, I don't think it's doing a service to resource estimation and kriging, in that, you know, the resource geologists on site are the ones who do the domaining and the pattern recognition. They know their deposit looks like a cat, and then the kriging sort of shades in between the domains and tells you whether you've got a Siamese or a tabby kind of thing. That's and so I guess in the machine learning aspect of having the cat is just removing the geologist.
True. Yeah. It's a good point. And I guess if you're using deep learning, you should use only with experts, local geologists who knows everything about the mine, about the geology, lithology, structural information, everything on mine site. So when you are applying deep learning, you should closely work with the expert of the data to understand how it works, because at the end of the day, you're using their data. You have to understand how it works. If it is well predicted, well designed, well constructed block model, where they incorporate a different number and type of data, I think deep learning will be better in terms of data quality. Yeah.
You're not precluded from putting geological interpretation into the data layers that go into the deep learning, though, are you? You can still add.
Yeah. So one of the ability of deep learning is to incorporate different types of data as well. So you can use not only structural information but lithological information as well, or any data you think is helpful.
Just wanted to get my notes straight here. Tom says kriging can be used to differentiate between a Siamese and a tabby. Yeah.
You can take that to the bank, Rick.
This is actually my cat Momo. Yeah, that's just generated by using ChatGPT. Yeah.
Okay, any last questions? Online people? Nothing. Okay. Thank you very much, everyone, for joining, and thank you once again, Nurassyl. We really enjoyed your talk, and you are welcome back anytime here to SMI. So yeah, let's thank Nurassyl again for his
Thank you.
talk today. And then next week we will have another seminar. It's going to be our second last one for the year, so it's only next week and then the week after that, and then we're done for the year. So yeah, hope to see you all there, and you are welcome to continue the chats with Nurassyl over a cup of tea and some cookies. Thank you.